I suppose I should have asked, are you okay if we record this?
Absolutely.
All right, now we have that. Now we have that recorded. So welcome to CC Colloquium for October 6th, 2021. We're excited to have a really, what I think is going to be really cool and fun talk about one of the cooler, funner missions that's going on and has gone on in a while. So we'll get to that in just a minute. Before that, announcements. The biggest announcement is tomorrow night, CC New Discoveries lecture series, The Universe Beyond Hubble. That's here tomorrow night at 7 p.m., but also online, right? So it's also in person and online? Oh, it's just online. It's just online. Don't come here. It's just online. So you can go to the CC website to get information, and I think Kim is also going to put a link to it in the chat. There'll be Roger Windhorst and a panel of other scientists and students talking about the Universe Beyond Hubble, and in particular, the James Webb Space Telescope, which launches soon, December 18th. Any other announcements? All right, so we will proceed to introduce our speaker. So Steve Ruff is going to formally introduce our speaker, and I will turn it over to him.
Great. So it is my pleasure to introduce someone whose bio and career I thought was inspiring and worthy of this colloquium. So she got on the list for that. She was born in Canada to parents who immigrated from Madagascar. And I thought that was pretty cool and kind of exotic to have parents from Madagascar and living in Canada. But she moved to Manchester, England, where in her teen years, she actually learned English as a second language from her native French. And so that was in Manchester, England. And then she went on to get an aerospace engineering degree from University of Cambridge. And that was followed by a PhD on the other side of the Atlantic at MIT. And it was during that period of time that she did no less than 3 internships, one at Goddard Space Flight Center and 2 at JPL. And it was during that first JPL internship that she witnessed the Curiosity rover landing on Mars. And that was clearly an inspiration. And she was determined then to work at JPL, which she managed to do with some perseverance, yes, after a couple of years landing a job there in 2014. So now we get to hear about Farah's adventures with perseverance and ingenuity from her work at JPL. So take it away, Farah.
Yeah, thank you for having me. Can you confirm that you can still hear me okay?
Yes. Yes,
okay,
can hear you.
Great. It's the joys of being remote. I'm like, am I talking to an open screen? Okay, so yeah, thanks for having me. So today I wanted to, share kind of the past few years with you, right? I'm a systems engineer on Perseverance. I've worked on the mobility system. I've worked on the mission during development. Now I'm one of the uplink leads doing operations, but I was also the integration lead for the Ingenuity helicopter. So did a lot of planning for the helicopter deployment and some of the initial flights. And so I kind of wanted to share that ride with you, share what it's about. I'm going to give a little bit of the background on the mission, just in case somehow you haven't heard of it or don't know the details, but kind of wanted to give you my flavor of the mission. So before I start, because I always like sharing embarrassing pictures of myself, kind of heard a little bit of my journey already. I was born in Montreal, grew up 40 minutes north of Montreal, and like every good French Canadian, I was a figure skater for 8 or 9 years. That's pretty much a rite of passage there. Moved to England, and that's where I learned English, and went to the University of Cambridge. And actually at the University of Cambridge, I was working on the aero side of aerospace, because the space industry in England just wasn't quite as strong back then. So I was working on jet engines, and I always kind of had this bug for space. I always wanted to be an astronaut. And it was always my dream to come to space and to come to aerospace on the space side. So at the end of my master's degree, I actually had a job offer from Rolls-Royce, which not the car company, but Rolls-Royce, the plane company. It's the same company that split in two, to work on jet engines. And I just had that bug. And so I decided to turn down a grown-up job to go to grad school. Immediately was like, why did I do that? Grad school is intense, but it was 100% worth it. And so I ended up doing my PhD at MIT, and then that's kind of where I was able to sort of live my passion. I did some internships at JPL and fell in love with the place. And I came out here in 2014. So it's been about 7 years now. And in addition to Perseverance and Ingenuity, I've gotten to work on the Marco CubeSats, which co-launched with InSight. They did entry, descent, and landing telecommunication for InSight. It was my first project at JPL. Then I actually worked on InSight. I worked on the seismometer as a payload systems engineer. And so I got to see that land in 2018, was part of the team doing operations. So this year was actually my second Mars landing, which sometimes I have to pinch myself to think like, wow, I've been here 7 years and I've been part of 4 Mars missions and 2 Mars landings. It's been a pretty awesome ride, and it's just been a wonderful place to work at. Let's see, I think I mentioned some of these already, that I worked on a number of Mars missions. One of the neat things with working at JPL is, even as an engineer, is that you actually also get to work on research and development and proposals. So I've actually worked a couple of discovery proposals. I worked a SMEX mission of opportunity heliophysics proposal called Sunrise that is now a real mission. So it's pretty rewarding when you get to come up with like, a concept and pitch it to NASA, and they're like, here's some money, go do it. So that was a pretty neat thing to be part of. And then I was also briefly on the asteroid redirect mission, which got canceled, but it was an interesting experience there because that interfaced with humans. And so I got to be exposed to that a little bit. Just come to show that, there's a lot of variety and things to choose from. Okay, so, today I wanted to talk about Perseverance and Ingenuity, but kind of wanted to give you, the context for where we are in Mars exploration, right? We started with Pathfinder and Sojourner all those years ago. Feels like forever ago, but it really wasn't. And then that was followed by the Mars exploration rovers in the early 2000s, Curiosity in 2012, and now Perseverance. And so, a lot of what you'll hear today and what we accomplished, we really are standing on the shoulders of giants. With every mission, we learn something, we develop something new, and then we build on that for the next mission. So it's always a little bit of taking what we've done before and then taking it apart and doing something completely new. And that's been the experience with Perseverance. It's supposed to be Curiosity's twin, but it's it's definitely the new car model with a lot of upgrades and then a flying helicopter. So it's been interesting to learn to balance a little bit of that of, okay, what do we keep the same and what are we doing that is new? And obviously Perseverance is part of the bigger Mars sample return mission. So now that we've collected a couple of samples and we're on our way to collect quite a few more, Mars sample return is becoming more and more real. And so the goal there is that these samples would get collected maybe in the next decade and come back to Earth. And we're also preparing for human exploration, which might not be so far away, we'll find out. But a lot of the work that Perseverance does, in addition to its prime mission, helps pave the way for human exploration. So, so definitely, part of the bigger picture of exploration at Mars. So hopefully you're familiar with what Perseverance looks like, but this is a CAD drawing of it. So as I mentioned, Perseverance is kind of it's the little sister of Curiosity because she's newer, but like every little sibling, she's actually bigger and has more bells and whistles. So the rover itself is very similar, but there were quite a lot of upgrades. The robotic arm, the end effector, has a number of instruments on it. It's got about 50 kilograms worth of instruments, which is quite impressive, including the coring drill, which is a drill that allows us to take samples. And then within the rover, which you can kind of see parts of it here, is the sample caching system, which is obviously very new for this mission. The sample caching system is a super complex beast. I would say that's probably just as complex as the rest of the rover. It has its own internal robotic arm and basically handles dispensing tubes, taking the tube back, sealing it, storing it, and all of that. In addition to that, obviously all the instruments were upgraded since Curiosity. We have new wheels, the new wheel design that does much better on the surface of Mars, and new cameras all over as well. A lot more cameras than Curiosity had, and they're all much better as well. So, so a little bit of the old and a lot of the new there. So a little bit of highlight of what the mission is about. Perseverance is an astrobiology mission, and this is the first astrobiology mission. And it's trying to figure out whether there was ever life on Mars and whether there might have been, it's looking for signs of ancient microbial life. So I'm sure I'm speaking to the choir here, and you know a little bit of the history of Mars, but you all know that Mars used to have an atmosphere and water and may have been a habitable place. And Perseverance is heading there, is there to figure out, could life have been there during that time? And so in order to do that, we obviously studying, geology and astrobiology and looking at our environment, but most importantly, we're taking those samples. And the reason why we have to do that, right, is because is there life on Mars is a huge question. You can't just answer it. It's a very hard question to answer. Viking had that issue when it first went to Mars of trying to answer that sort of astrobiology question, and it came back with, well, we don't really know. We can't be sure with the instruments that we have. And some papers out there, I think that things were found, but the burden of proof is really on the people investigating Mars to prove that there's life, and it's extremely difficult to do solely in situ. So being able to take a variety of samples and bring them back to Earth are really what's going to enable their our analysis of what's happening there. And as I mentioned as well, we're preparing for humans, and there's a few ways that we're doing that. So here's a little bit of an exploded view of Perseverance. What is in there? It's a little bit of an older picture. That the wheels are actually the old wheels, but that's okay. You understand the gist. So as I mentioned, there's a number of instruments on the arm, spectrometers, imagers, things like that. And then there's some instruments on the mast as well. I'm sure you're very familiar with Mastcam-Z, but we also have some engineering cameras there, and SuperCam, which is has a laser and a microphone up there as well. And we have a weather station. Every mission at Mars recently has had a weather station to measure pressure, wind, temperature. All of those things are important, not just as contextual evidence, information for our measurements, but also as information for, again, understanding, preparing for humans at Mars. The other two instruments that are sort of a little bit more focused on preparing for humans is RIMFAX. Obviously, RIMFAX is a radar. It's studying the structure right below the surface right below the rover, but that is going to be essential information if we're ever going to send humans at Mars, in addition to the science experiments it's doing, of course. And then there's MOXIE, and as was mentioned, I went to MIT, so I'm maybe a little bit biased because I think MIT's MOXIE is really cool, and it's one of the it's a jointly developed with MIT. But MOXIE is a technology demonstration. It's not really a science instrument per se, but MOXIE demonstrated that we can extract oxygen from the Martian atmosphere. It actually happened, the first time they did it was the same week as we flew the helicopter for the first time. So that was a big week. I'll always remember it. But the Martian atmosphere is mostly carbon dioxide, but they demonstrated that they can extract that oxygen. And that will obviously be something that's very important for astronauts, because when you're trying to launch things, any additional mass, it's an exponential factor with the amount of fuel you need. So if you don't have to bring all that oxygen, and you can pre-create some on Mars, not only for humans to breathe, but also as fuel, that becomes, an enabling technology. So yeah, in addition to all those instruments, we also carried another mission with us called Ingenuity. So Ingenuity is its own project, and it's the Mars Helicopter project, and that is also a technology demonstration mission. And its goal was to demonstrate the first powered flight on another planet. Now, you can already imagine that operating things on Mars is kind of hard. There's light time delay. Signal to get from Earth to Mars takes anywhere between 12 and about 25 minutes, depending on the time of year. So that makes operations complex in addition to the environment. But to fly on Mars is a whole nother ballgame. Mars is about 1/3 of the gravity of Earth. So you'd think, yeah, it's lighter, so it should be easier to fly. But it only has about 1% of the atmosphere. And so when we're talking about lift and our lift to weight ratio for a helicopter, it's a lot harder to fly on Mars than it is on Earth. And so Ingenuity is only about yay big. It's the size of kind of a big tissue box. The blades are about 4 feet long, and they spin incredibly fast, and that's what allows it to fly. But of course, when you're trying to do something that's so mass constrained, that was definitely a challenge to build that helicopter. And I'll show you a lot of what we achieved, but it's definitely incredible to see it work on Mars. Okay, so another thing I think that people don't always realize is kind of the scale of how long it takes to build a Mars mission and how long it takes to get to Mars. Mars is the second closest planet, so we're lucky that it's not that far, but it still takes a little while to build all these things because we had to invent some of these technology, right? The sample caching system, for example, all of these things took time to develop. So the idea for Perseverance, came along around 2012 after Curiosity landed, and folks were thinking, okay, what are we doing next? Can we use this technology that we've developed to do something else that's incredible? So the two things were happening in parallel. The science team was defining their science goal, choosing that site, and Jezero Crater was chosen back in 2018. And it's not a real picture of Jezero Crater, obviously. Well, it's a real picture, but the coloring is not real. And the coloring is for composition. And so they chose Jezero Crater because it's an ancient river delta. And so obviously, if you have goals of astrobiology, going to a delta is incredibly interesting. One thing, however, and I can show you on the next slide, is Perseverance has landed in a place that no other mission really has landed before. And if you look at the picture, it doesn't really look like a safe place to land. And so one of the enabling technologies that were part of the Perseverance mission was that for the first time, we were able to implement terrain relative navigation. And I'll show you the video of landing again, but you'll see as we were landing, essentially the rover had a camera and was able to compare the images it was seeing to onboard maps and also make assessments about potential hazards and then decide on a safe place to land. And so that technology is going to be really essential for human landings or future Mars missions or even other missions to other planets, because it allows us to go to these much more interesting places, these much more featured places without having to necessarily drive, dozens of kilometers to get there. So that's how we were able to get there. And then, as I mentioned, in parallel with that, the design and build started of the rover, and that took about 6 years to build. So the scales when you're talking about missions like that are pretty impressive. I came from, Marco, which is a CubeSat that I think we built in a year and a half or something like that. And some of those parts may or may not have been ordered from Amazon type of thing, to, this huge flagship mission that is highly, highly complex, where you are partnering with industry all over the US and institutions all around the world to get it built. So it's definitely a different beast when you're trying to build that. So I wanted to show you this video here, and I'm going to mute it, but of what it looks like at JPL. Why do we build those things? If you haven't been there, just to get kind of contextually, what does it look like when we build a rover? So what you're seeing here is that's the crew stage, and the engineer is working on it. This is, it goes by fast. So let's see, right here is the crew stage. That's what got us to Mars. Right here would have been the solar panels. This is where the fuel went. And then this is also part of the crew stage. This is the housing that the rover was in during its journey to Mars. Inside it, you can see actually the sky crane installed. And this is the sky crane, which dropped us off on the surface of Mars. And then you'll see kind of a series of tests that happen during development. And those are mostly in the last couple of years. So it was just on a vibe table. Some things you don't think about is these things are massive. And so getting them even transported across lab is quite complex. The test that was happening here was a solar insolation test. So we put in a special chamber and mimic the sun to see, you know, the thermal effects of that particular phase of the mission. And then this is also a thermal vacuum chamber. So after this test, they closed the door, pulled a vacuum, and tested the spacecraft in that environment as well. There's also a number of, this is when Moxie was installed, but there's a number of functional tests that have to happen. Can we deploy things? Can we move the arm? This is how wheels are built. So that was built in-house as well. And this is how a mobility system's installed. But what you can see is that it's really, it is a team of people that make this happen from day to day and from months over months to get this thing built. Truly a team effort. This is the RTG. And then in addition to building the actual rover, what you saw here was some of the functional testings that have to happen. And so, you know, we had to test out the drill system, make sure all of that was going to work. And so we have Earth replicas of pretty much every piece of the rover where we do some of that testing. So it really takes quite the village to get this built together. And again, if you haven't been to JPL, this is kind of a picture of where it all happens. This is our clean room, the spacecraft assembly facility. So I like this picture because you have the rover, the cruise stage, the descent stage, which is the sky crane, and then all of the other equipment that we need to get all of that testing done. This room is really special. It's kind of neat actually when you work at JPL because you can just go up to the gallery on any day and go see what's happening. If you ever come for a tour, this will definitely be one of the places you'll see. But what's neat is on this back wall here is our wall of fame, which is all the missions that have been built in the spacecraft assembly facility. And since the very beginning of JPL, that particular building has been used to build spacecraft. So it's a little humbling when you walk in there to work on your rover or your mission to see, you know, the history of everything that's been built there. I have to admit that I haven't stopped by SAF since we landed. I'm assuming that our mission badge is up there, but I'll have to go check it out and take an updated picture here. Because it was, you know, you don't get your picture up there until you make it to where you're supposed to be going. So we'll see if that's showing up yet. But one thing that's particularly neat, you know, especially as a younger engineer is, I mean, I love to share this picture, you know, of people taking a selfie and kind of enjoying what they've achieved. But these people are my friends. And to me, like, that is just incredible that, like, my friends and I built a rover that went to Mars. Like, that is literally what we did, right? And to me, that's just so incredible. You know, I don't think I had quite realized that was the job of an engineer when you went to JPL or NASA. It's kind of like I never imagined that part of it. I don't know why. I think you know, conceptually you think, yeah, those are the people that landed a rover on Mars and they did that, and you see them in mission control, but you never get to see them like that as a team, kind of enjoying things, enjoying what they've done, and figuring it out together. I mean, the amount of late nights or days that we were like, look at something and be like, huh, what happened here? What? We got to fix this. And you know, and it was mentioned that one of the reasons why I fell in love with JPL was because of the Curiosity landing and seeing those people land that rover on Mars. And it's kind of crazy now because I get to work with some of those people and sometimes tell them they're wrong, which is kind of scary. But so it's just an incredible feeling to say, like, yeah, I've contributed to this thing that is now on Mars and that is now asking what the biggest existential question that humanity has ever had, right? So So if that's not selling you on how much I love my job, I don't know what else would. But it's just been such a pleasure to be part of that team. So for me, as I mentioned, I was part of the mobility team for the rover, and specifically, I was the flight system engineer for the surface attitude positioning and pointing system, or SAP. And so what do all these words mean? Essentially, my job was to make sure the rover doesn't get lost on Mars. Thankfully, it doesn't move that fast, so not that easy to get lost. But you know, one of the challenges when you're on Mars is you don't have GPS, you don't have local maps, and you always have to know, you know, what orientation the rover is in, how it's going to point back its antenna to Earth, where they are with respect to Earth, where Earth is in the sky at any given time, because Earth is rotating and Mars is rotating, and all of that navigation process. And so, so as part of the mobility team, I specialized on that, but helped out with a lot of the testing that had to happen. And so one of my favorite tests during what we call ATLO, which was Assembly Test and Launch Operations, was our first drive. And so if you can imagine, this drive is the only one we did with the rover before going to Mars. It was a few days after my birthday in December 2019. And it's the only one we saw with our own eyes, because the next one was on Mars. So this test, just to not paint just the rosy picture of engineering, this test was meant to take 3 or 4 hours. It took us 10 hours and we didn't get it all done. So sometimes, you know, when you get to, you know, we thought we were ready, we had done all of our software testing, but once you get to having the entire system there all together, things just interact a little differently. Things were looking weird, and so we had to pause and take our time. And so that's just kind of the nature of the job. It was still incredibly rewarding, and I you know, always remember that day. And of course, we achieved everything that we wanted to achieve. But just to kind of give you some insight of, sometimes things don't go your way. That's okay. Okay, so then our launch happened. Well, somewhere in that, COVID happened. So we all went and worked from home and started supporting a lot of that testing from home. Although we were still going to lab from time to time, because when you're interacting with hardware, obviously you have to be there. So we actually shipped the rover to Kennedy Space Center in February of 2020, so a little bit before COVID. And the plan was at KSC, we were going to spend a few months doing our final testing and assembly, get, you know, the power source, which is nuclear, on, install the sample caching system, which we wanted to keep clean for as long as we could, so they delayed installing it, things like that. So this, for example, you know, just to give you an idea of what the rover is doing, one of the things that we have to know is where the center of mass is of the rover. So this is a rotation table that allows you to define that. And then eventually we made it and assembled the whole thing. I love sharing this picture, and I call it the Amazon packaging of Mars missions, because what you're seeing here is our tiny, tiny rover. It's not tiny, in the launch fairing of a launch vehicle. And, you know, when we launch spacecraft to Mars, we use commercially available launch vehicles. And those are typically designed for big, you know, geostationary satellites, big Earth rotating satellites. And so, you know, they don't need to go as far, they don't need as much delta V, and so so they can be a lot larger for the same amount of fuel. When we go to Mars, we need all the fuel that rocket offers, but not necessarily the volume. And so that's why it ends up looking like this, but it makes for a funny picture, because we look so much smaller than the rocket actually does. And so we launched right on time on July 30th. I watched the whole thing from home because I didn't feel comfortable traveling to Florida at the time. And it was a little bit of a bummer to not be there in person. I'd seen InSight launch, but I hadn't, you know, seen this much bigger rocket out of Florida. But I got to still share the experience with my friends and enjoy that day. But, you know, about an hour after launch, we were back to working. And our cruise to Mars, we started our cruise to Mars, which lasted until our landing day, February 18. So, so that was sort of a 7-month cruise to get there. And during that time, we had to continue testing, but we also test the humans. So when we do operations on Mars, you know, our rover had to be ready, and it was ready because we launched it. But our people also have to understand how to operate a Mars rover, and I'll show you some of those intricacies later. But so we spent a lot of our time doing what we called operations readiness tests to prepare to certify our operators to operate things on Mars. And we also did testing in the Mars yard during that time. And so we have two vehicles that we use for mobility testing. So we have Scarecrow, which is about 1/3 of the mass of Perseverance. So it has the same weight as Perseverance has on Mars. And so we do a lot of like the slip testing and things like that using Scarecrow. And then we have OPTIMISM, which is the Earth version of Perseverance that we use to do all of our functional testing. And we spent a lot of time doing that. And we actually have a saying at JPL, which is test as you fly and fly as you test. So we definitely spent a lot of time doing that. One of the things you're seeing here is the video from one of our operations readiness tests while we tested the helicopter deployment. And so we went out in the Mars yard, made an environment that was similar to where we, you know, the type of environment where we might deploy the helicopter, and tested not only the deployment sequences, making sure that we could deploy it, clear it properly, but also tested, again, the humans, right? How do we build the drive if we're operating this remotely? How do we make go, no go decisions and things like that? So I was in charge of a lot of that planning, and it was pretty fun actually to get to put together these tests and these scenarios for people using our software, and then seeing how people interact with the rover and the helicopter for the first time. Okay, so we landed on Mars on February 2018, and I'm going to play this video. I'm hoping you've seen it before, but this is the day that we landed on Mars. And one of the incredible things with the landing day is that we had additional cameras on Perseverance this time around. And so we were able to see the supersonic parachute open. As we entered, we had a shield that slowed us down and protect us from the heat. And then what you're seeing here is that shield being released, and then the terrain relative navigation system doing its job at looking at the surface of Mars and deciding on where to go. And for me, I think I've watched this video maybe like 1,000 times at this point. But it's every time I still get chills. You know, you have to put yourself in the shoes of the people that are in that room. They've spent 6-8 years on this mission. You know, I'd spend a little bit less, and this 7-8 minutes had to go right for us to be able to do our job, right? Like I was gonna know by the end of it whether I had a job for the next 6 months, you know, year or not. And every single part of it is automated when you're landing at Mars, because you know, we communicate with the rover radio. Radio is an electromagnetic wave, and so it travels at the speed of light. And the light time delay from Mars to Earth on landing day was about 12 minutes. So conceptually, if you imagine that when we got the first data that the rover was entering the surface of Mars, it takes about 7 or 8 minutes to land. That data was about 12 minutes old. That meant that the rover was actually already on Mars. We just didn't know whether it was safe or not. And there was really nothing we could do but watch it all happen. So I'll fast forward a little bit here as we see the landing. But you know, I can still remember, for example, when we got some of the imagery from the sky crane come back and the rover being landed on Mars. Like some of this is like, it's so incredible. And I'm like, is this really real? Like this happened at Mars, right? Like it's hard to imagine this happening. But it was so incredible to see those pictures come down and eventually those videos of the entire thing. And so glad that we were able to do that and share that with everyone. But definitely an emotional day, one of the highlights of my career, and I'll always remember it. This is what I look like. Just as excited as everyone else. I was in the surface operations room at JPL, which is upstairs from the big landing room that you saw in the video. And actually that picture on the left, I remember the day that I pulled it up. We were doing our downlink assessment, and you know, these pictures and videos came down a few days after landing. And the first time I saw it, it actually, took me a while. Sorry, I dropped my phone. Took me a while to figure out what was going on there and what I was looking at. So and then obviously the entire team gathered around my screen, being like, "What did you find? What came down?" And so that was pretty cool to see as well. So once we got on Mars, the real work began, and we started doing surface operations. So as I mentioned, I do a little bit of downlink analysis, analyzing the data that comes down from the rover from day to day, but I mostly focus on the uplink. What do these words mean, right? So when we do Mars operations, we don't just joystick the rover, right? I already explained Mars is too far away, and lifetime delay would make it incredibly boring if we were waiting for each command to come back. So what we do is called tactical operations. So every night at about 4 or 5 p.m. Mars time, the rover sends us back a bunch of data about what it did that day. The downlink team analyzes that data and figures out how the rover's doing, how the activities went, and then passes that information up to uplink. Uplink as a team plans the next day. It's essentially like building a big piece of code for the rover for the next day. And we plan every single step, like down to the minute, down to the second of what the rover is going to do. There's some things that the rover can do in an automated way. We have something called AutoNav, which allows it to drive in a particular direction or towards a particular goal autonomously. So that's one of the things that we have been using. And then eventually in the next year or two, we have something called onboard planner, which will allow the rover to sort of fill in the gaps in activities and decide what activities to do itself. So we're going towards more and more automation, but especially early on in the mission, it's very manual and intensive as we learn about our rover and finish commissioning it. So we did something called Mars time for about 68 sols. Let me explain what that means. So I mentioned that, you know, we get our data down from Mars at 5 p.m. Mars time every day, and we analyze our data, and then we have to uplink our plan before 9 a.m. Mars time the next morning. The rover wakes up around 9:30, gets all its data, decides what to do for the rest of the day. So, okay, that's fine. I somehow got a PhD to work the Martian night shift. I'll get over it, I guess. But here's the complication. A Martian day is 24 hours and about 30 minutes, just over 30 minutes. So that means that on a given day, 5 p.m. on Mars might be 5 p.m. on Earth for me, but then the next day it'll be 5:30. The next day it'll be 6:30. And, you know, so your day sort of kept marching to the right every day, which meant that I, like every good engineer, had a Google Doc that told me what time to get up, what time to go to sleep. It set my alarm for me for the next day. I shared it with my family so that they knew when they could call me. Shared it with my boyfriend so he would know kind of what meals I was, you know, eating at what time. There's definitely days where, you know, I would be waking up at 11 o'clock to go to work. I've been found drinking a cocktail at 7 a.m. and claiming that it was 5 p.m. for me because it was, and my bedtime was going to be 9 or 10 a.m. So it's definitely a strange time, made even weirder by COVID. But, you know, there were definitely nights where when I wasn't on shift, you kind of stay on Mars time. It's really difficult to swap back and forth. And took my dog for walks at 3 in the morning. He wasn't too happy about it, but kind of got over it. He was pretty happy, actually. He had someone to nap with at pretty much every time of day. But it was definitely a challenging time. But it was needed because we needed to be able to operate the rover every day and really, you know, babysit it over those first 2 and 3 months or so. Now what we do, by the way, is called something called adjusted Earth time, where when the Mars night lines up with Earth daytime, we work during the day. And so our shift start time will shift anywhere between sort of like 6 a.m. to 3 p.m. is about when we're allowed to start. And so we can work as late as midnight or 1 a.m., but, you know, it's mostly human hours. And then when Mars daytime and Earth time daytime, well, Pacific Earth time line up, then we work every other day, more or less. Or we go into something called restricted, where we use the previous day's information to plan. And so that's how we get around not living like zombies for the entire mission. And of course, the rover has a little bit more automation, and we are a lot more confident with planning, which helps. So in the next few minutes here, and I want to make sure I keep time for questions, there's so much to talk about. I want to show you some of my favorite pictures from the mission, or videos as well. So this here, I told you was part of the mobility team, was the picture of the first drive on Mars. And it was a pretty simple drive. They drove straight and then turn around, and this happened kind of like the first week on Mars. But the reason why I like this picture, and I think it's so cool, is because the tracks start out of nowhere, right? We landed, you can see the landing site right here, and the tracks, they just end. Like, that is it. This just, we came from the sky and then started driving, right? And you know, conceptually, again, these are things that you internalize, and you know that's what's meant to happen. But until you see those pictures, it's quite incredible when you see that for the first time. And so for me, that was obviously something that I'd been looking forward to, making sure that our drive would go successfully. And since then, we've driven, kilometers at this point. So that has been going very well. I also mentioned that I was in charge of coordinating the drop off of the helicopter on the surface of Mars. So Ingenuity was tucked in below the rover, and about a month into the mission, we found a suitable area to deploy it. And so that took a series of steps to separate the helicopter. We checked in on it every day, making sure that it was going through all its steps. And then once we dropped it off on the surface of Mars, we had to drive off of it. Within a few hours, actually, we didn't really even have ground in the loop, because we wanted to expose its solar panel and make sure that its batteries would recharge before the Martian night. So I was in charge of developing that whole concept of operations, making sure that we didn't drive over the helicopter, making sure that we would drive off of it and that it would survive, that we would hear from it. And it all went incredibly well. But for me, these pictures are, these three pictures here, the story of my life for the first couple of months on Mars. That third picture you're seeing on the right is the first color image that Ingenuity took as soon as we dropped it, before we drove off of it. So you can actually see the legs and the wheels here. This is the wheels of the rover, wheels of the rover, legs of the helicopter. Next here, it's going to take a second to load, is the famous selfie. It is also my desktop background that we took of Perseverance and Ingenuity. A little bit of a backstory there. There was really no science drive for that selfie, but a few of us on the rover team just, curiosity knows how to take selfies. We have a very similar system, so we figured we can probably figure out how to do this. And we just thought there was no other time in humanity that there would be, that there would be a rover and a helicopter next to each other. And it was such a historical moment. So a few of us kind of snuck into the test bed whenever it was free, and developed the sequences and developed the capability, and kind of, we would whisper to each other that we were doing this, and then eventually kind of came to the project and said, hey, can we spare a day to get this done? Wouldn't it be important to do this? And we're ready to do it if you want. And all of that, sneaking around paid off, because the project bought into it. Just to give you an idea though, when you take a selfie on Mars, we have an imager called Watson on the robotic arm. And, it's not like when you take your phone and you just take a selfie and you're done. What you actually have to do is a series of pictures, and it's over 60 images that you take, and you take it in rows and then build a mosaic, the same way as it is when we build our 360 images. So it actually took a couple of hours to take that selfie, and then a couple of days to get it down to Earth. But I mean, it is still to this day my favorite picture from any Mars mission, and it may continue to be, just because it has such an importance for me of all the work that had to go into getting that helicopter on the surface of Mars, getting to listen to it, positioning ourselves to take that, and then also the significance that it has, moving forward in that mission. So as I mentioned, the goal of Ingenuity was to perform first powered flight on another planet, and here it is. So April 4th, 2021, we took off from the surface of Mars. And this is a 5-meter flight, and then we did a rotation and landed back down. So it's a very humble flight. It was only about 30 seconds, but I cannot tell you how many things went into this day. I mean, we deployed the helicopter, we commissioned it. We actually had some issues during commissioning with a software bug that then we had to go test a workaround. We had to figure out where we were going to image the helicopter from, even to get this video, the timing and stories that go behind. How do we make sure we're pointed the right way, that we time, this is a 30-second flight, that we time it properly so we catch the flight? How do we make sure that we get all of these images down so that we can confirm that the flight happened? It is hundreds of people's worth of work just to make that video happen. But I mean, was it worth it, or was it worth it, right? And of course, since then, we have done quite a few more flights. I'll play some of these here for you. So we've done so far a total of 13 flights with Ingenuity. The technology demonstration goal was to only do 5. Turns out it overachieved, and we were able to do a few more here. I like this middle flight. This is flight number 3, where we kind of fly out of frame and then come back. And so Ingenuity has entered a new period called the Operations Demonstration Mission. And so at this point, we're using our Return to Earth camera, which is this beautiful color camera. And what Ingenuity is doing now is it's actually acting as a scout for the rover. And so we're trying to figure out, can we, is it feasible to bring a helicopter with us, operate it kind of at low cost, and inform the rover's decisions, figure out if there's interesting places to go, places that are not so interesting that we might want to avoid. This picture on the left, I really love as well from Ingenuity, because what you're seeing in this picture, Ingenuity is up in the air. You're actually seeing the landing site up here, and then Perseverance right here. So, and we've gotten a few snaps of Perseverance from Ingenuity. So it's not just Perseverance taking pictures of Ingenuity. We try to return the favor as well and take pictures of Perseverance. Let's see here, a couple more. And then obviously during all that time, I have been fully engrossed in Ingenuity and getting that to fly. And then I still continue to support surface operations, of course. And during that time, we have explored so much of the planet already. We've driven, as I mentioned, I think a couple kilometers. And then very recently, earlier in September, we took our first set of samples. So you might have heard that when we took our first sample, didn't quite go as expected. The sample most likely broke off. Mars throws curveballs at you. It's not exactly what you expect. It's one of those like, oh, we've never seen this in testing on Earth. And it's like, well, that happens, right? It's not quite the same. So we ended up with an atmospheric sample, which is still actually going to be really useful for sample return. But we were recently able in early September to take our first sample, our first core. What you're seeing on the right here is that core inside the tube. So we have an imager inside the rover that takes an image of that sample in the tube before it gets sealed. And then the science team actually decided to take 2 samples of that same rock, so call it a paired sample. So that's the first of many samples that we're hoping to take. And just to finish, what's next for us? You might have heard me talking a little bit earlier before the talk started that we were currently in conjunction. So conjunction is the time when Mars, as viewed from Earth, is on the other side of the sun. So when Mars is behind the sun or close to the sun in the sky, there's plasma noise that's created by the sun, and that prevents us from sending radio signals to Mars. And so basically the rover's taking a 2-week vacation. Most of the team is actually on vacation or working on upgrades to some of our systems. And then we should be hearing back from it. We've been getting sort of a trickle of data from time to time, but we will be hearing back from it full time, pretty much this time next week, a little bit later than this time next week. And to give you an idea of what we've done so far, we landed here at the Octavia Butler landing site, traveled south. This is sort of an area of interest called Zeta. So this is, the science team decided to investigate the crater floor and understand, they're seeing things that looked like delta remnants. And so understand the context for where it is that we've landed and how that ties into the bigger story of the delta. And then we've been traveling up north here towards this southern area of Zeta, and we've just entered that region here. And so we'll continue once we come back in October, exploring this region. We'll take probably at least 2 more samples and possibly pairs of sample. That's our goal before the end of the year. And then after in the new calendar year, our goal is to sort of go on a road trip and go on a drive campaign, drive back around on this more benign terrain. It's sort of really difficult to cross. So we'll take the long route and then head up towards Three Forks and then towards the Delta, which is where we're very excited about the geology and things that we might find. So I'm just going to leave, actually a couple more pictures I wanted to share with you. Sort of mentioned that for me, this is kind of a dream come true as an engineer. So on left here is the picture of me as an intern. And, this is when I fell in love with Mars exploration and curiosity. And so for me, it's really been a pleasure in coming full circle to work on this mission, but also wanted to show you that these missions, it really takes a village. And so here's just the JPL people that work on this mission. There are thousands of people across the world and across institutions that have contributed to this mission or will contribute to this mission over the coming years. And one of the things that I find exceptional with missions like Perseverance and Ingenuity and Curiosity is that when you build such complex systems, there isn't a single person on Earth that fully understands that system. And I find that fascinating. And for me, that's one of the huge motivations for working on missions like this is I'm part of something that is bigger than myself. And that took a lot of teamwork, a lot of communication, a lot of coordination, all the skills that as students we learn. But it is so incredible to say that as a team, as a society, we were able to build something incredibly complex and perhaps answer one of the biggest existential questions that we've had of are we alone and is there life elsewhere? And that happens as a team. And so I kind of wanted to leave you with that message because all of you at some point in your life will this is something that you will experience. And sometimes it is frustrating to work as a team. It's not always rosy, but when you achieve things like this, it makes it all worth it. So I'm going to leave you with a few resources, of the key websites to look at, Twitter accounts, Instagram accounts, websites, all the things that you can find more resources. And let's go ahead and take questions. I have time. I know I talked for longer than I thought I would, but I can spend the time answering any questions as long as you need. So let's see.
So we have a few minutes for questions. So if you have any questions, please put them in the Q&A if you're online. And otherwise, we have people with hands up in the audience here. So Rick's got the microphone out there. So we'll take a question from the audience. We have a couple of people here at least with their hands up.
Hi, first of all, it's a very good talk. I mean, I really enjoyed it. I was at the edge of my seat the whole time. And I just wanted to ask you, you mentioned the RIMFAX antenna prepares for humans. So what exactly does it do that enables it to prepare for humans?
So a little bit out of my expertise, but my understanding of what it's doing in addition to just generally looking at the composition, one of the things that we're interested in eventually, right, is if we're going to be building anything on Mars or building any kind of resources for astronauts on Mars, we're going to need to understand contextually what the ground looks like, what it's made of, and there's of course interest in understanding whether there might be systems under the surface of Mars, like tunnels and things like that, although that's a little bit deeper under the surface of Mars. But so it starts to answer that question of what is Mars made of, what's the composition, is this something that that we can build on, what would that look like? But that is my very limited engineer's understanding of what RIMFAX is doing.
We have a couple of questions online, so we'll ask one of those. How close can the rover get to cliff faces? Can it reach under ledges to recessive strata?
So we have to be careful. So the rover can drive to about a tilt about 30 degrees. So it can't just go up, go up a cliff face or anything like that. And we obviously have to be careful of, if we see features, for example, we're going to stay some distance away or inch closely, the same way as a human would if they were next to a cliff. So that's our limitation as a rover. And then in terms of reaching things with the robotic arm, again, it's a question of what we can see and the clearance, right? We can, the arm has multiple degrees of freedom, and it can reach out and extend and go around features if we have the imagery. But depending on what you might be looking at, that's really going to be the limiting factor. We can, however, drill both horizontal and vertical. So we have that capability. If there was sort of a face that we were looking at that was really interesting, we'd have the ability of drilling a sample that way as well.
Great, thank you. There's a question in the audience, I think.
Hi there. Does Ingenuity have the capability of exploring Mars outside of Jezero Crater? If so, how far?
So one of the limitations with Ingenuity is that it is leashed essentially to Perseverance. It needs Perseverance for communication. It doesn't have the ability of talking to Earth directly. So whenever we operate it, we send all of our commands from Earth to Perseverance, and then Perseverance essentially acts as a very, very expensive relay to send our information to Ingenuity. So we haven't quite tested the edges of how far Ingenuity can go, but we have experience, as we get further away. We've been 200-300 meters from Ingenuity and experienced kind of like the drop in telecom performance when that happens. So typically we try and maintain not quite line of sight. At first we thought we would need line of sight. We don't, but we can only be about 200 or 300 meters away. Now we've done flights where we've flown away from the rover and come back. And so that's certainly an option to sort of toe dip into places and come back so that we can reestablish a comm once we're back. But unfortunately, we're really tied to Perseverance.
All right, a couple more questions if you have time. I'll do online one, and then when building the rover, does the landing site near a river delta impact the design? Were you expecting softer sand, difficult areas to traverse and have to adjust it, or was it designed sort of generically for Mars?
So it was definitely designed specifically for this terrain. And by that, what I mean is it's not necessarily the fact that it's a delta, but the fact that there were so many obstacles in this terrain. If we'd taken Curiosity and the Curiosity landing system and sent it, we couldn't have landed at Jezero Crater. It just wasn't safe enough, because when we land the traditional landing system that Curiosity had is we establish an ellipse, and we know that we can target the landing system to wherever in that ellipse, but we don't know where in that ellipse we're going to land. So that was true for Curiosity. That was true for InSight as well. So we have to guarantee with the older landing systems that it was going to be safe to land anywhere there, and our rover wasn't going to be upside down or at a super high tilt or on top of a boulder and be permanently damaged. So when it came to Perseverance, because the science team was interested in going to this river delta because of the incredible things that I'm sure we'll find there, we had to design, we had to implement this terrain relative navigation system. So that system was especially designed because of where we wanted to go. And that's what allowed us to say, okay, well, it's not all safe in that ellipse, but there are safe places. And we're going to design a system that will allow the rover to essentially, have an astronaut or the equivalent to be able to divert us and divert into a safe area. So the system was designed to go where the science team wanted to go.
All right, great. So the landing system was specific. So last question, Steve Roth.
So this is going to test your knowledge of Ingenuity. I have a very specific question about Ingenuity, something I've always been curious about. It has 4 legs with feet on the end. One of the feet is different than the other 3. It has this funny little sort of hook-like thing. What's up with that?
Hook. It's actually part of the deployment system. The hook was where the foot was tied to the rover. So that's why the cable cutter was going through that hook.
While it's kind of attached to Perseverance, that's one of the points of attachment through that hook?
Yeah, essentially it was used to attach it to the rover, and then So it has no significance anymore, but it was needed as part of that system, of that deployment system.
Cool. You
But
passed the
good,
quiz.
good eye.
In-
It's rare
Ingenuity's
that people
belly button.
notice that. Yeah. Also
Ingenuity's
helps
belly
us.
button. It serves no purpose except it did once.
Yeah, exactly. Yeah, that's a good way to
All right.
put it. It's also a good way when you look at images, it gives you an idea of the way the helicopter is oriented, but that was not the goal. The goal was really just for that deployment.
Thanks.
Great. Well, thank you very much. That was awesome. That was a great talk. We really appreciate it. I'm sorry we can't get to all the questions that are online. But thank you very much again for taking the time to give us an insider's view on one of the most exciting missions in a long time. Thank you very much.
Yeah, happy to. And not sure if you saw
So-
Jim's note in the
Right.
in the
Jim Bell
chat.
posted a note that the first peer-reviewed paper is coming out tomorrow, right? In Science. Is that what he posted?
There's a press release tomorrow.
Yeah, press
so yeah,
release tomorrow
it's
for the
very
first
exciting.
peer-reviewed paper coming out from the mission. So this is very timely.
Yeah.
Thanks again for taking the time. We appreciate
Yeah,
it.
thanks for having me. Have a good rest of your day.